This video lesson, we're going to be looking at something called the real number system, which is basically the system of numbers we use in everyday life. So our goal is not only to understand how to classify numbers in this real number system, but really to more importantly understand the evolution of the real number system. Now what I mean by the evolution is this. If you go back in history, you'll find that older civilizations didn't start off with all the same numbers that we use today. We're in a much more complex society and we have to represent more complicated numbers. But back in the day, some civilizations could get by with just what are called the natural or counting numbers. And I think of counting numbers because it's the numbers I can count on my finger and then beyond. So 1, 2, 3, 4, 5. And then if you keep going endlessly, these are the natural or counting numbers. And for older civilizations, this was fine. I could keep track of 1 item or 2 items or 3 items or 20 items. And this system worked. So for a while, that's all there ever was. And it wasn't really until later on where some civilizations started using what's called positional notation that there started to be a problem. Like, for example, positional notation is the same thing as trying to describe the year of 2001. And the problem is they call it positional notation because each number in a certain position represents a certain amount. So the 2 represents 2 thousands. The 1 represents 1 1. But the zeros, well, this represents 0 hundreds and 0 tens. But if you'll notice in the natural counting numbers, 0 didn't yet exist. So to create this positional notation system, someone had to introduce the idea of 0. And so natural or counting numbers evolved into this. All the natural or counting numbers plus 0, which then got renamed as the whole numbers. So there isn't a lot of difference between the natural numbers and the whole numbers except for 0. And so for a while, this was fine. We started to be able to do certain things like basic mathematics. 1 plus 3 equals 4. Uses all the numbers in the whole number system. 3 minus 0 equals 3. And again, I'm using all the different whole numbers that I know to exist at this point. But then another problem came up. What about this problem? 1 minus 4 equals what? Well, we know it's negative 3, but at the time, negative 3 wasn't a part of the whole number system. So somebody realized that, you know what? We need to introduce the idea of negatives. And so the whole number system expanded out to this. All the whole numbers, but then all of their opposites. Negative 1, negative 2, negative 3, negative 4, going on forever. And so this became known as the integers. The integers are the whole numbers and their opposites. And so this allowed them to do problems like this one, 1 minus 4, and get negative 3. And so we introduced this idea that negatives could be a part of the number system as well. So again, looking at some of the math we could do, negative 3 times 1 is negative 3. Uses all my different integers here. 4 divided by negative 2 is negative 2. Once again, using all the integers that are listed. But then, again, a problem came up. 3 divided by 2. Well, 3 divided by 2, well, we know it's 1.5. But if you notice, 1.5 doesn't yet exist in our number system. So once again, the number system evolved to include all those partial numbers in between all of the integers. Now, of course, this isn't a complete list, but I'm just mentioning a few. Negative 2 1/4, a half, 2.81, 3.3 repeating. These are all numbers where they have these partial pieces, the decimals or fractions. And so once again, things were renamed, and this is now the rational number system. And a way to think of it is the reason why they call it the rational number system is the word ratio. And so any number that can be written as a ratio or a fraction is considered a rational number. Okay, so for example, 1/2 of course is a fraction, so it's definitely a rational number. 3.3 repeating, even though it's written as a decimal, can be converted into 3 1/3, so it can be written as a fraction. Even the numbers that we already used, like 2. 2 can be written as a fraction. We don't normally do it, but 2 can be 2 over 1. And so this became the rational number system. So for a while, everybody thought, this is a complete list now. We can do all the different types of math problems that we need to. But then somebody found out there was another problem. That we started to use numbers like we're using now, square roots. square root of 17, you get this 4.123105, blah blah blah. Goes on forever, but not only goes on forever, there's no pattern to it. Now another famous number like that you were probably familiar with is pi. 3.14159 goes on forever, and again, no pattern. And here's just a random one, 2.417605, blah blah blah. Again, assuming it goes on without any kind of discernible pattern. And so because these went on endlessly with no pattern, there's no way to write these as fractions. And so they had to come up with not another evolution of the system, but an add-on. That there was this whole separate group of numbers called the irrational numbers. And so these are numbers that can only be written as a non-terminating decimal, meaning a decimal that goes on forever that has no pattern. Now the no pattern part's important because, for example, going back a screen, 3.3 repeating, this goes on forever, but it has a pattern. And that can be expressed as 3 1/3, whereas these don't have any type of pattern, and that's what makes them irrational. Now, I think this will make a lot more sense if you take a look at it as a chart. So let's take a look at the next slide. So if we start off like before, we've got the natural numbers. Things we can count on our finger and beyond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, so on and so forth. And so that was the initial start of the number system. Then the idea that, well, you know what? We're going to need 0. 0 is an important number, so let's add 0 on to the natural numbers and we'll reclassify this as the whole numbers. So the whole numbers is nothing more than 0 plus the natural numbers. Then the idea that, you know what, sometimes we need to express things in terms of negatives. And so all the opposites of the whole and natural numbers were added on, which became the integers category. And notice how it's a box within a box within a box. So integers isn't just what's here in red. Integers is all these numbers plus 0 plus the natural numbers. Whole numbers include 0 and the natural numbers. So this is more like a Venn diagram. A box within a box, or a category within a category. So next came rational numbers. Rational numbers were, of course, situations where I needed to describe partial numbers, a half, negative 0.4, things like that. And so anything that could be written as a fraction. And then finally realizing that some things could not be written as fractions. And that gave us the irrational numbers. Now notice how the irrational numbers are a separate group from the rational numbers. These are all the numbers that couldn't be described in this system and then were just kind of outside of that Venn diagram. So pi or any decimal that went on forever with that pattern. And so all these put together is what we call the real numbers system. Okay, so this is what you're going to use to classify numbers. So for example, some sample problems to finish off. Let's just take our chart here and take a look. Let's say I'm trying to classify 12. So first off, I need to decide, well, is 12 a part of the rational or irrational group? Now 12 doesn't have a repeating or an endless decimal, so it must be in the rationals category. And if I think about rational numbers, yes, because I can write 12 as 12 over 1. But let's see if I can go deeper into this category. Could I consider it an integer? Well, yes. It fits in this integer category because if you think about it, 12 is also a whole number and it's also a natural number. So since I can place 12 that deep inside my Venn diagram here, that 12 counts as a natural number, a whole number, an integer, and a rational number, but not irrational. Alright, let's take another one. Negative 7. Now once again, negative 7 doesn't have an endless decimal, so it's definitely not an irrational number. So it probably belongs in our rational number category, which makes sense. I can write negative 7 as a fraction, negative 7 over 1. But then is it an integer? Yeah, it's the opposite of one of our whole numbers. Okay, but is it a whole number or a natural number? No. Okay, because whole numbers and natural numbers don't include the negatives. We don't start including the negatives till we hit integers. So the deepest I can take this into my chart is into integers. So we would consider negative 7 a rational number and an integer, but not a whole number and not a natural number. Alright, how about this one? A third. Now, I mentioned this before on the other slide. 1/3 as a decimal is 0.3 repeating. So it is an endless decimal, but it's an endless decimal with a pattern, which still does not make it irrational. Well, it is a fraction, so it is a rational number. Would we consider this an integer, a whole number, or a natural number? No, because it's a partial number. Integers, whole numbers, natural numbers don't include these partial numbers, and so the deepest I can take 1/3 into my Venn diagram is rationals, and so it only fits into one category. Okay, finally, let's take a look at this one. 2.8173314 blah blah blah. An endless decimal with seemingly no pattern, which means that fits over in the separate category of irrational numbers. And so this is how we classify numbers under the real number system. We take a look to see where it fits in our Venn diagram, and we categorize it accordingly. All right, good luck with your assignment. See how you do with the real number system.